This video is going to take us through developing the geometric series formula and then how to use that formula to solve questions involving geometric series. We've already talked about arithmetic, sequence, and series. The difference between the sequence and series is that a series is the terms added together. So only difference here is that it's the terms of a geometric sequence added together. Couple important reminders about this. Make sure that in your series you have plus signs in between rather than commas. That's going to become important when you expand for a sigma notation, let's say. And what makes this geometric is that if we go from one term to the next, our ratio is 3. Remember, you can get that by doing second term divided by first term, third divided by second, and so on. Why do we need this? Our geometric series are in a lot of practical applications, such as radioactive decay, which is important for environmentally, physically in our world, and also interest payments, which is something that would concern you with your investments or with our economy and different things. Before we get started on the problems that occur with the series, we are going to just take a quick look at a proof of the formula. First thing I'm just showing you is the written out version of what would happen if we had that, like 2 plus 4 plus 6 plus 8. So the first term is our A1. Our second term is, so we had, technically this is 2. You don't have to write this down. Plus 2 times 3, which is 6. The next one, the reason it's r squared is we're multiplying by the ratio again, so it's really like saying r times r. Remember, you're adding the exponents to get that r squared. So it's really 2 times 3 squared, which would give us 18, if I'm looking at that sequence above. Now, I don't have a last term in that sequence, but with our formula, this is our an formula right here. That would be a1 times r to the n minus 1. Now what we're going to do to develop the formula, we want to really get rid of all those middle terms. So we're going to multiply the entire series by r. I'm going to erase some of the stuff that I did already just so that you can see what's going to happen next. So I multiply by r, and now I'm going to subtract those two things. When I subtract, we're going to have a lot of things that cancel out, and I kind of lined it up for you. So if I do Sn minus Rsn, we can't combine those yet because there's 2 different variables on there, so I just write that. A1, we bring it down. Oh, sorry. That's supposed to be one nice line with an arrow. Okay, so we bring the A1 down. Then the A1R cancels. Goodbye, goodbye. The A1R squared cancels. Now when we multiplied by r, the reason why we have a1r to the n at the end is if I were to multiply those two things together and add the exponents, the ones would cancel. So that's why we get the r to the n. So everything cancels out. The n minus 1 would be right before that. Everything cancels out except for the a1 and the a1r to the n. So we bring that down also. Our fourth step is factoring out common multiples, GCFs. So we factored out the Sn and the A1 from either side. The goal is to get an Sn formula like we had for the arithmetic series, obviously very different than that formula. We're going to divide both sides by the 1 minus r to get our final formula. Now I'm going to just rewrite the formula slightly differently. I'm going to put one big parenthesis. So we're going to have A1 on the outside, a nice big parentheses, and do 1 minus r to the n over 1 minus r. It just makes it easier because you can do everything inside the parentheses and then multiply by a1 at the end. So it's a very quick proof, which is why we usually show it. And The one big difference with the formula than a lot of the other formulas is we have r to the n and not n minus 1. So when we go to do the examples, that's something you'll want to be careful with. And we're going to take a look at our examples in our next video.